Greetings to the respected faculty. I am Lasya Mandapati from CSC AI&ML B section. My roll number is 24951A6686. And today I'll present I'll be presenting on the topic scale up or scale out for graph processing under the subject design and analysis of algorithms. Graph processing has become one of the most challenging problems in the modern computing because real world graphs such as social networks, web graphs, and transportation network contain billions of nodes and edges. Traditional algorithm models assume manageable data sizes, but modern graphs exceed single machine capacity. This presentation explores how algorithm design must adapt to large scale computation. The central question is whether it is better to scale computation by strengthening a single machine, known as scale up, or by distributing work across many machines, known as scale out. The, deci- the decision affects algorithm complexity, communication cost, memory access patterns, and overall efficiency. Now, graph processing is essential for applications such as search engines, recommendation systems, biological networks, and traffic analysis. These systems require fast traversal, short path computation, and ranking algorithms over extremely large datasets. The challenge is not just algorithm correctness, but scalability. As graphs grow, computational bottlenecks shift from CPU speed to memory access and communication overhead. Algorithm design must consider hardware architecture as part of the complexity model. Scale up and scale out represent two different strategies for handling this growth. Understanding the trade offs is crucial for designing efficient graph algorithms in modern computing environments. Graph processing involves performing operations on vertices and edges to extract meaningful structure. Common algorithms include breadth first search, depth first search, page rank, shortest paths, and community detection. These algorithms are irregular in nature. Unlike matrix operations, graph workloads involve unpredictable memory access and data dependencies. The irregularity makes parallelization difficult. From an algorithmic perspective, graph processing stresses both time complexity and memory complexity. Efficient graph algorithms must minimize communication and maximize locality, which directly influences scaling decisions. Modern graphs easily exceed terabytes in size. A single machine cannot store or process them efficiently. Even when memory is sufficient, bandwidth becomes a bottleneck. Graph algorithms require frequent access to neighboring nodes, causing random memory patterns. In distributed systems, this leads to network communication overhead. Therefore, scalability is not just about adding hardware, it requires algorithmic restructuring to reduce data movement and synchronization cost. Choosing scale up or scale out determines how these trade offs are handled. What is scale up? Scale up means increasing the power of a single system by adding CPU cores, memory, GPUs, or faster storage. The system uses shared memory architecture where all processors access the same memory space. From an algorithm perspective, scale up systems simplify design. Algorithms behave like parallel shared memory programs, avoiding expensive network communication. This approach is effective when graph fits into memory and synchronization overhead is minimal. Many high performance graph libraries rely on scale up machines for efficiency. The main advantage of scale up is low communication cost. All threads operate within the same memory environment, enabling fast synchronization. Algorithms are easier to debug and reason about because shared memory models resemble classical algorithm design. Cache locality improves performance when data is structured carefully. Scale up systems also reduce distributed failure risk and simplify consistency management. For medium scale graphs, they often outperform distributed systems due to lower overhead. However, scale up has strict physical and economic limits. Memory capacity and processor speed cannot grow indefinitely. High end machines are expensive and energy intensive. A single system also creates a single point of failure. Most importantly, extremely large graphs cannot fit into even the most powerful machines. Once memory limits are reached, performance collapses. This makes scale up unsuitable for web scale or social network scale datasets. Scale-out refers to distributing graph computation across multiple machines connected through a network. Instead of relying on one powerful system, the graph is partitioned into subgraphs that are processed in parallel. Each machine handles a portion of the vertices and edges, and communications occurs through message passing. From an algorithmic perspective, this introduces a new dimension of complexity. In shared memory models, access is local. In scale out systems, access becomes remote and network latency replaces memory latency as the bottleneck. Partitioning becomes a central algorithmic problem. A good partition minimizes cross machine edges while balancing load. Poor partitioning leads to excessive communication and idle processes. Thus, scale-out graphs, scale-out graph processing is not just about adding machines, it requires designing algorithms that minimize communication routes, exploit locality, and tolerate partial failures. The primary advantage of scale-out is its ability to process graphs that exceed the capacity of a single machine. By, di- by distributing memory and computation, scale-out systems can theoretically scale indefinitely by adding nodes. This horizontal scalability is essential for real world graphs such as social networks, web crawls, and biological networks. Scale out systems also provide fault tolerance. Distributed frameworks replicate data so that node failures do not crash the computation. From a complexity standpoint, scale out allows parallel execution across thousands of processes. Algorithms such as PageRank define from iterative distributed processing, where each node computes partial results. Another key benefit is cost efficiency. Instead of expensive supercomputers, scale out systems use clusters of commodity machines, making large scale graph analytics economically feasible. Despite its scalability, scale out introduces serious algorithmic challenges. Communication overhead often dominates computation time. Every time an algorithm requires information from another partition, a networked message must be sent. Graph algorithms are communication heavy because vertices frequently depend on neighbors stored on their machines. This results in synchronization delays and increased runtime. Load imbalance is another issue. Real world graphs are often skewed, meaning some partitions receive more work than others. Idle processors reduce overall efficiency. Additionally, distributed systems must handle failures, message loss, and consistency issues. Designing algorithms that remain correct under asynchronous execution is non trivial. Therefore, the theoretical speedup of scale out is limited by network constraints and algorithmic design. From the perspective of algorithm analysis, scale out systems require a new complexity model. Traditional time complexity is insufficient. We must consider communication complexity, synchronization routes, and data locality. In distributed graph processing, the cost of sending a message may exceed the cost of computation. Algorithms must be redesigned to reduce cross partition communication. Techniques such as graph partitioning, vertex replication, and asynchronous updates are used to improve efficiency. Many distributed frameworks adopt bulk synchronous parallel model where communication proceeds in synchronized rounds. Thus, algorithm design becomes architecture aware. Efficiency depends not only on algorithm logic but also on how well it matches the underlying hardware. Different graph workloads favor different scaling approaches. For example, BFS and DFS on moderate graphs benefit from scale up systems because shared memory minimizes synchronization overhead. However, large scale ranking algorithms like PageRank or community detection require scale out systems. These algorithms operate on massive graphs where distributed memory is essential. Graph structure also matters. Dense graphs may favor scale up due to heavy communication requirements, while sparse large graphs benefit from scale out. This shows that scalability decisions are workload dependent. Algorithm engineers must analyze graph size, density, and access patterns before choosing an architecture. Modern graph systems increasingly use hybrid architectures that combine scale up and scale out. Each distributed node is itself a multi core shared memory system. This approach reduces communication overhead with nodes while still enabling large scale distribution. Hybrid systems exploit both intra node parallelism and inter node scalability. Frameworks such as distributed graph engines often adopt this model to balance communication and computation. The goal is to maximize scale. The goal is to maximize locality while maintaining scalability. Hybrid architectures represent the practical future of large-scale graph processing. In conclusion, scale up and scale out represent two complementary strategies rather than competing ones. Scale up offers simplicity and low communication overhead, making it ideal for medium sized graphs. Scale out enables processing of massive data sets but introduces communication and synchronization challenges. The key insight is that algorithm design must adapt to architecture. Efficient graph processing depends on minimizing data movement, balancing workload, and exploiting locality. Future systems will likely combine both approaches, supported by hybrid architecture and architecture-aware algorithms. Understanding these trade-offs is essential for designing scalable graph algorithms. Thank you for your attention. This concludes my extended discussion on scaling strategies for graph processing. I hope this presentation showed how algorithm design and system architecture are deeply interconnected. Modern graph analytics is not only a theoretical problem but also an engineering challenge. Thank you.